Hi students, in this video we will study how to design a half adder. So what is an adder? The basic elementary operation is addition of two binary digits. So binary numbers has two bits only, 0 and 1. So for the addition there are four possible elementary operations. That means we can add 0 with a 0, we get the output as 0, or we can add 0 with 1, we get output is equal to 1. Then 1 with 0, output is equal to 1. Then when you add 1 with 1, we get 0, sum is equal to 0 and carry is generated. This carry is actually carry forward to the next bit. So this 0 is the sum and 1 is called the carry. Okay, so for the first three elementary operations, there is only one output, but for the last operation there are two output, sum and a carry. So for adding two numbers we have two inputs and also two outputs, because for the last combination we have two outputs, sum and a carry. Okay, actually for first three operation carry is equal to 0. Right? So next we design a half adder. What do you mean by a half adder? Half adder means a circuit that performs addition of two bits. A combinational circuit that performs addition of two bits is called a half adder. So our aim is to design a half adder. It is a combinational circuit. So this is the statement of the problem. Design a circuit that performs addition of two bits. So that is the first step. So second step is we have to identify the available inputs and the required outputs. So here we have to add two bits. So we have two inputs. Okay. When you add two bits from the previous elementary operation, we have first three combination we have one output and the last combination we have two outputs. So generally we have two outputs. Okay. So here we have two outputs. So third step is assign label for this inputs and outputs. So the inputs are labeled as X and Y, and outputs are labeled as S and C, where S is the sum and C is the carry. Right? The next step is draw the truth table. Okay, truth table is actually specify the relationship between the inputs and the outputs. So here we have the truth table with two inputs XY and two outputs sum and carry. So this XY is the input and S and C is the output. Right? So two input variables, there are four input combinations, 0 0 0 1 1 0 1 1. Okay. When you add 0 with 0, sum is equal to 0 and carry is equal to 0. When you add 0 with 1, sum is equal to 1, carry is equal to 0. When you add 1 with 0, sum is equal to 1 and carry equal to 0. When you add 1 with 1, sum is equal to 0 and carry is equal to 1. So this is the relationship between the input and output. So we have the truth table. Right? Next we can write the Boolean expression for each output variable from the truth table. Okay, so here S is equal to one output for only two minterms, that is 0 1 and 1 0. So we can write it as X bar Y plus X Y bar. Okay, X bar Y plus X Y bar. Then carry is equal to 1 for only the last combination, that is XY. Next step is minimize the Boolean function using K-map. Okay, so here we can draw the K-map for both S and C. So this is the K-map for sum and this one for carry. Okay, so here we have the variables X and Y. Y may be 0 or 1, X may be 0 or 1. Here also 0 or 1, 0 or 1. Okay, we can mark the minterms. So here minterm is equal to for 0 1 and 1 0, here for 1 1. Okay, so here not possible to group the ones, here also only 1 1. So we get the simplified expression as same. S is equal to x bar y plus x bar y plus x y bar. Actually x bar y plus x by y bar is equal to x XOR y, right? Carry is equal to xy itself. Clear? Next we can draw the logic circuit for these expressions, right? So first we can implement this using basic gates. So here x bar and y bar, so we have to first note that inputs. So here it is x, here we have the x bar, okay, then y input, both are ANDed together, we get x bar y, so here it is y input, then y bar, so we take y input, okay, then note that y, so we get y bar, then we take x input, then both are ANDed together, so we get x y bar, then over these two outputs, okay, that is x bar y plus x y bar. Okay, next we can draw the circuit for carry, that is C is equal to xy. So here we have x input, this is the x input, so take that x input, okay, this one is the y input, so take that y input, both are ANDed together, so here we have the xy, so this is carry xy and this is the sum x bar y plus x y bar, right? So this is the implementation of the half adder using basic gates. Clear? Then here actually x bar y plus x y bar is x XOR y, so we can draw the circuit using XOR gate and AND gate. So that circuit is, here we have the XOR gate, the inputs are x and y, okay, so here we get x XOR y, then we take x input, then ANDed together, so here we have xy, so this is carry and this is sum. Okay, clear? Next we can implement half adder using universal gate, that is first using NAND logic. Okay, so here the sum expression is equal to x XOR y, so we know how to implement XOR gate using NAND logic. Okay, refer the video implementation of all other gates using NAND logic for getting that expression. Okay, so here x XOR y, we can, from that video we get the expression as x into xy whole bar into y into xy bar whole bar whole bar. This is the expression for the XOR gate using NAND logic. Okay, then C we can write as xy, so xy can be written as xy double bar, right? Next we can draw the circuit. So here we have NAND gate with x and y are input, okay, so here we get xy bar, right? Then this x is NANDed with xy bar, so here you get x dot xy bar whole bar, then this y is NANDed with this xy bar, here you get y into xy bar whole bar, right? When you take these two inputs ANDed together, okay, so here the output is x into xy bar whole bar into y into xy bar whole bar whole bar, so we have the sum value. Okay, Then what is carry? Carry is x by double bar. So here we have the xy bar. Take that output, okay, then complement it. So here given to a NAND gate, so here we have x bar whole bar. So here we have the expression for the sum, and here it is carry. So this is the NAND gate implementation of the half adder, right? Next you can implement this half adder using NOR logic. Okay, so first we can take the carry, that is carry is equal to xy, that is written as xy double bar, that is equal to apply De Morgan's, that is equal to x bar plus y bar whole bar. Then we can take the sum is equal to x bar y plus xy bar plus x bar plus y bar. Apply distributive law for the first and third term, that is x bar into x plus y plus y bar into x plus y. Then apply distributive law for these two terms, that is x plus y into x bar plus y bar. So this can be written as x plus y into x bar plus y bar double bar. Okay, apply De Morgan's, that is x plus y bar plus x bar plus y bar whole bar, right? So here we have carry is equal to x bar plus y bar whole bar. Here also one term is same as carry, so you can easily implement this circuit. Okay, so that is, first we can draw the circuit. So first we can take x and y inputs given to a NOR gate. So here you get x plus y whole bar, right? That is x plus y whole bar. Then x and y inverted. So here you have x input, take that x input, complemented using NOR gate. So here you have x bar. Same way take y, complement using NOR gate. Okay, so here you have y bar. Then these two NANDed to node together. Okay, so you get x bar plus y bar whole bar. Then take x plus y whole bar and x bar plus y bar whole bar, then node together. Okay, so here you have the output x bar plus y bar whole bar plus x plus y whole bar. Okay, that is the sum. Next we can take the carry, that is carry is x bar plus y bar whole bar. So here you have x bar plus y bar whole bar, so this one is the carry. Okay, so this is the sum and this one is the carry. This is how half adder is designed. So, and the implementation of half adder using basic gates and universal gate, that is NAND logic and NOR logic. Okay, thank you for listening.